Hi everybody, welcome to lecture 28 of Electrical Engineering 331. This lecture will be devoted entirely to reviewing some problems that are similar to problems we had on some of our early daily tests. To be honest, these problems are so similar to some of the earlier problems that we've done that I think that it could be argued that you should know how to do all of them already, and so I think it would be an excellent opportunity for you to look at these problems and try to solve them first before looking at the solution that I will present, and that would, I think, help you to identify which areas you need to concentrate on. But anyway, having said that, let's go ahead and jump right into this. Our first example says, suppose that x of t is as shown here, and each square on this graph paper is 1 unit. And so we ask, what is xe of -2? Now you might remember that xe is the even part of the function and xo is the odd part of the function. And the formula for finding xe is that xe is equal to 1/2 x of t plus 1/2 x of -t. On the other hand, xo of t would be equal to 1/2 x of t minus 1/2 x of -t. But in this case, we're calculating the even part, and so we need to find out an expression for x of t. And then once we find the expression for x of t, we can get one for x of -t, and then we can substitute those two expressions into this equation and get xe of t, and then finally evaluate that expression at t equals -2. So that will be our strategy. Okay, so the first step then is to find an expression for x of t, and you can see that it goes down here at -3, it goes down 2 units. So that's -2 of u t plus 3. It's u because you see how this is constant. After it goes down, then it's constant. So this is why we have u there, -2u of t plus 3. Then at 0, it jumps back up, so that's why we have +2u of t. And then after jumping up, it starts to ramp up with a slope of 1. We can see it's a slope of 1 because it goes up 3 in a horizontal distance of 3. So that's +1 r of t. And then after that, it flattens out. So we have to subtract from that r of t minus 3 right here to make it flatten out. And then to make it go from here down to the axis, we have to subtract 3u of t minus 3. So this is the entire expression for x of t. And then to get x of -t, which of course we need right here in order to find xe, in order to get x of -t, well, that's very simple. We just substitute in -t for t in this expression for x of t. And so you can see that we've done that, compared these two lines, and you can see that everywhere we have a t in this line, we have substituted -t in this line. Now we have x of t and x of -t, and remember xe of t is 1/2 x of t plus 1/2 x of -t, and so we just brought the 1/2 out in front, and then we have brackets, and here on this line we have x of t, and on this line we have x of -t. And so now we're ready to evaluate that. We want to find xe of -2, and so let's do that. when we substitute in t equals -2 everywhere in this lengthy expression, we will get this expression right here. And fortunately, that's, even though that's a long expression, it does simplify a lot, because u of -2 we know is 0, r of -2 is 0, r of -5 is 0, u of -5 is 0, r of -1 is 0, u of -1 is 0. So the only non-zero terms are -2 u of 1, which we bring down, nothing else on this top line, and then on the bottom line, -2 u of 5, which we have right here, plus 2 of u of 2, which we have there, plus r of 2, which we have there. And that's it. Those are the only non-zero terms. And so now we go ahead and evaluate those terms, and u of 1 is 1, so -2 times 1 is -2. U of 5 is 1, so -2 times 1 is -2. U of 2 is 1, 2 times 1 is 2. And then find the r of 2 is equal to 2, so we have a 2 here. And so this is 1/2 times -2 plus -2 plus 2 plus 2, or 0. So xe of -2 is equal to 0. Now let's look at another example. Find a period of x of t equals cosine of pi over 7t plus pi over 4 minus sine of pi over 3t. Okay, and our strategy for that, for doing this problem, is if we can find some number, capital T, that is a period of both of these, then it must be a period of the difference as well. So that will be our strategy, is to find some number that is a period of both of these. Well, in order to be a period of the first expression, it must be the case that pi over 7t is equal to 2n pi, where n is an integer. And in order for capital T to be a period of this second expression, it must be the case that pi over 3 times t is equal to 2m pi, where m is an integer. Okay, so we have these two equations, and t must satisfy both of those equations. We can simplify both of those equations. We can solve both the equations for t, and we get t equals 14n here, and here we get t equals 6m. So if t is equal to both of those, then we can set them equal to each other. 14n is equal to 6m, or 14 over 6 is m over n, which means m over n is the same thing as 7 over 3. We can pick any m and any n that satisfy that equation. So let's pick the simplest. Pick m equals 7 and n equals 3. Okay, well, if n is equal to 3, this equation would give us t equals 42, and likewise, if m is equal to 7, this equation would give us t equals 42. So t equals 42 is a period, and any integer multiple, a positive integer multiple of t, like 84 or 126, would also be periods of this function. Okay, so now let's look at equation 28.3. Here we're asked to evaluate the integral from a to b of e to the t cubed times delta of 7t plus 1 dt. And you can assume that a is less than b. Okay, so for these problems, what we need to do is to get the argument of the delta function as a single variable, which I've called u in this case. So I'm going to let u equal 7t plus 1, and so du is 7 dt, which means that dt is du over 7. Okay, now once we use this substitution, then let's see what the integral becomes. Well, when t is equal to a, since u is equal to 7t plus 1, u will be 7a plus 1. So the lower limit becomes 7a plus 1. Similarly, when t is b, u is 7b plus 1. So the upper limit is 7b plus 1. E to the t cubed, well, t is u minus 1 over 7, so that becomes e to the u minus 1 over 7 cubed. Then delta of 7t plus 1 becomes just delta of u, and dt becomes du over 7. So I'll pull this 1/7 out here in the front, and then for the rest of it, I will observe that as long as u equals, as long as this, where u is equal to 0, well, excuse me, as long as we're the argument of the delta function, which is u, as long as that point is in this range, then the value of the integral is simply the rest of the integrand evaluated at u at that point where the argument is equal to 0. So in this case, then that tells us that we will have e to the, again, u is equal to 0, so we have minus 1/7 cubed. E to the minus 1/7 cubed is the value of the integral. Oh, and times 1/7, don't forget that. That's the value of the integral as long as 7a plus 1 is less than 0 and 7b plus 1 is greater than 0. Because again, the point where the argument of the delta function goes to 0 must be between these two limits. Otherwise, the value of the integral is 0. Okay? And then as a final step, what we could do is simplify this, since our original problem was expressed in terms of a and b rather than in terms of 7a plus 1 and 7b plus 1. It would be convenient to convert this restriction here into restrictions on a and b, and we can easily do that by just subtracting 1 all the way across and then divided by 7. So we get that the integral is equal to 1/7 e to the minus 1/7 cubed if a is less than negative 1/7 is less than b, and 0 otherwise. And let me just emphasize what this notation here means is two things. A is less than negative 1/7 and, underline and because both conditions must be true, A is less than negative 1/7 and B is greater than negative 1/7. So that's what this means. If that's true, then the integral is equal to 1/7 e to the minus 1/7 cubed. If that's not true, then the integral is equal to 0. Now let's go to another example. And let's see, I believe yes, this is our last example, but this one is a little bit longer. Okay, so our last example for this test is the following. It says we have a function x of t which is equal to t to the n u of t minus 1. And we want to know for what values of n is this an energy signal, for what values of n is it a power signal, and for what values of n is it neither. Okay? So as usual, we'll first look to see what would be necessary for this to be an energy signal. And remember, what we have there is to integrate from negative infinity to infinity of x of t squared dt. Or if you prefer, you can think of that as the limit as t goes to infinity of the integral from minus t to t, if you like it like that better. Okay, so substituting in for x of t, we have this. And when we square that, that just means we have t to the n u of t to t minus 1 times t to the n times u of t minus 1. That's what we mean by squaring, is we just multiply it by itself. Okay, well, t to the n times t to the n is t to the 2n, and u of t minus 1 times u of t minus 1 is simply u of t minus 1, because it's always equal to 1 if t is greater than 1, and it's always equal to 0 if t is less than 1. And of course, 1 times 1 is 1, 0 times 0 is 0. So when we multiply this function by itself, we just get that function. So we have this. And then we know from our previous work with with the integrals that have u in the unit steps and the argument, what we can do is just modify the limits on the integral and then take the u function out. And so that's what we've done here. Since this function is equal to 0 for t less than 1 and it's equal to 1 for t greater than 1, we will get this. Okay, now at first glance you might say, well, this is a very easy integral, and in fact it is, but you need to be careful about one thing. So you have 1 over 2n plus 1 t to the 2n plus 1 from 1 to infinity. That's what you would probably write automatically if you saw this integral. But you need to be careful, because notice that if n is equal to negative 1/2, then this would give you a 0 in the denominator. So the negative 1/2 case you have to evaluate separately. And so this expression is only good if n is not equal to negative 1/2. But if n is equal to negative 1/2, well, notice then that this becomes t to the negative 1, or in other words, 1 over t. And we know the integral of 1 over t dt over these limits would just be log of t, the natural log of t from 1 to infinity. And that's what we get if n is equal to negative 1/2. Okay, so now let's think about what happens with these. Well, let's look first at the second thing. This will become log of infinity minus the log of 1. And the log of 1 is 0. So this is just log of infinity. That's what we get if n is exactly equal to negative 1/2. But now, in the other case, where n is not equal to negative 1/2, we have this expression, and it needs to now be broken up into two different cases. Because if 2n plus 1 is positive, then infinity raised to a positive power gives us infinity. So that's why we have infinity if 2n plus 1 is greater than 0. But on the other hand, if 2n plus 1 is less than 0, then we have t raised to a negative power. And so when we raise infinity to a negative power, we're going to get 0 at the upper limit. At the lower limit, we're always going to get 1. So we would have 0 minus 1, which is negative 1. And so we would get negative 1 over 2n plus 1 if 2n plus 1 is less than 0. So this breaks up into these three cases. And so x of t equals t to the n u of t minus 1 is an energy signal in these two cases here. In the upper case, it's not an energy signal because we're getting infinity. But in these two cases, no, not this case either, because log of infinity is infinity. Okay, so not this case either. So it's only this case. Only this case right here is an energy signal. And notice that this case, you could take, you could add negative 1 to both sides and then divide by 2, and that says n is less than negative 1/2. So only the middle case is the energy signal. Okay, only the middle case gives you an energy signal, and that middle case is the same as n is less than negative 1/2. N equals negative 1/2 doesn't work because of the log of infinity, and n greater than negative 1/2, which is the same thing as saying 2n plus 1 is greater than 0, that one doesn't work either. So only n less than negative 1/2 will give you an energy signal. Okay. So now that we know that, now we go back and say, well, What if n is greater than or equal to negative 1/2? What do we have then? We know it's not an energy signal in this case. Is it a power signal? Well, remember, to determine if something is a power signal, you need to look at the average power and see if it's finite. Now, remember that if a function is a periodic signal, to look at the average power, you just look over one period. But this is not a periodic signal, so what we do is we look at the limit as t goes to infinity of 1 over t times the integral from minus t over 2 to t over 2 of x of t squared dt. Okay. Well, we already have found out that x of t squared will give us this, so we don't have to go over that again. And we know that the u of t minus 1 can be taken care of by changing the lower limit to 1. That's just like we did before, so still nothing new there. And so now we can go ahead and evaluate the integral. And as before, we will have 1 over 2n plus 1 t to the 2n plus 1. And that's what we will get if n is greater than negative 1/2. But remember now, we're looking at the cases n is greater than or equal to negative 1/2. All we took care of up here was n less than negative 1/2. Those were the energy signals. But we still have the possibility down here that n is equal to negative 1/2. So we have to consider that one. Again, we have to consider it separately, because when n is equal to negative 1/2, this is the integral of 1 over t dt. So we would get then log of t. But now the limits are 1 and t over 2. Okay, so one more time then. If n is strictly greater than negative 1/2, we have this. But if n is exactly equal to negative 1/2, we will have this. Okay, so now let's go ahead and evaluate both of those terms. Up here, the 1 over n plus 1 can come outside of the limit, because this is a limit on t, and there's no t in the 1 over n 2n plus 1, so it can come out. And we're left with limit as t goes to infinity of 1 over t, and then when we evaluate this at the upper limit, we'll get t over 2 to the 2n plus 1, and at the lower limit, we get minus 1 to the 2n plus 1. On the other hand, when we look at this second term, we will get limit as t goes to infinity of 1 over t, log of t over 2 minus log of the lower limit, which is 1. And now, for this upper expression, all I've done in going from here to here is just to observe that t over 2 raised to the 2n plus 1 power is the same thing as t to the 2n plus 1 divided by 2 to the 2n plus 1. That's the only thing I've done in going from there to there. And the only thing I've done in going from here to down here is to make the observation that the log of 1 is 0. So I can drop that out. Okay, so now let's see what happens. Well, this t, when we multiply it through by both terms here in the parentheses, remember, this is 1 over t is t to the negative 1. So when we multiply t to the negative 1 times t to the 2n plus 1, we just get t to the 2n. And then at the bottom, we still have this 2 to the 2n plus 1. And then when we multiply 1 over t times negative 1, we get minus 1 over t. So that's what we'll have for this upper expression. And then for the lower expression, we can go ahead and evaluate that limit. Now, it's true that as t goes to infinity, the log of t over 2 will go to infinity. But as t goes to infinity, this denominator is going to infinity much more quickly than the numerator is. And so that's why the limit as t goes to infinity of 1 over t log of t over 2, that limit is equal to 0. So that's why we get 0 down here. And for this expression up here, what we can say is that if 2n is positive, which of course happens when n is positive, if n is positive, then this term, well, actually, let me start over and say this. Let's observe something easier first. As t goes to infinity, this second term goes away, so we don't have to worry about it at all. So we just have to worry about this first term. And if n is positive, then we have infinity raised to a positive power, and that will blow up, and we get infinity if n is greater than 0. But on the other hand, if 2n is less than 0, which means n is less than 0, then we would get infinity raised to a negative power, which would be 0. So we'd have 0 here and 0 there, and we would get 0. And that's, again, that's if n is negative. And remember, we know that n is greater than or equal to negative 1/2. We're not considering anything else, anything other than that, because we've already taken care of that above. So there's only one more case to consider here. We've considered n greater than 0 right here, and here we considered n less than 0. So the only other case to consider is if n is equal to 0. And if n is equal to 0, then this would just become 1. And then down here we have a 0, so that would be 1/2, so that would be 1/2. And if n is equal to 0 out here, that's just 1, so 1 times 1/2 is 1/2, if n is equal to 0. So we are getting, for the, remember, this is the average power here, and so the average power is finite in these two cases, but it's infinite right here. So we have a power signal if n is equal to 0, or if negative 1/2 is less than or equal to n is less than 0. So we can put those two together and just say this is a power signal if negative 1/2 is less than or equal to n is less than or equal to 0. And so we can sum up all of our results right here. Remember, number 1 said, when is it an energy signal? It will be an energy signal. This signal right up here will be an energy signal if n is less than negative 1/2. It will be a power signal if n is between negative 1/2 and 0, inclusive of the endpoints. And it will be neither if n is greater than 0. And notice one thing that's interesting about this problem is that if n is greater than or equal to negative 1/2, but less than 0, then the average power of the signal is 0. And that's sort of interesting, because you might be tempted to believe that if the average power of a signal is 0, then it's an energy signal. But we know that it's not an energy signal. So you might think, well, how can it have infinite energy, but it has 0 average power? And that's because as we go to infinity, the total amount of energy is increasing, but it is increasing more slowly than t is, and so therefore the average energy is 0 in those cases. But in this case, the middle case here, when n is equal to 0, here the average power is 1/2. So it's just, this is sort of an interesting case. But anyway, those are the answers to this problem. So that gets us started with reviewing some of these concepts from the early daily tests. And I think that you will now be prepared to do the work on test 28. So good luck.